So here's more about infinitesimal rotations, a tiny introduction to basically Lie groups and Lie algebras in a very, very specific context. So last time I talked about how if you've got a linear map from Rn to itself, basically just think of it as multiplication by a matrix, A. The claim is that as long as the output of that matrix, when you put in a vector v, is perpendicular to v for all inputs, then that's actually going to be an infinitesimal rotation. Certainly, I did show that if you have a family of rotations and you look at what it does infinitesimally, just the derivative, when it's just starting out, it did have this property. I proved that. I didn't prove the converse, that this is really sufficient. Okay, and I'm not going to. But let me just give you a very basic example. Two quick basic examples. I did already talk about how in 2 dimensions this is a rotation by theta. It's very easy to take the derivative of that. Taking the derivative of a family of matrices, you just do it entry by entry. Derivative of cosine is 1. Derivative of cosine is sine, which is 0. Derivative of minus sine is minus cosine, that evaluates to minus 1. Derivative of sine is cosine, which is 1. And derivative of cosine is sine, which is 0. Okay. And note what's true about this matrix is it's anti-symmetric. That is, its transpose is equal to minus itself. That's going to turn out to be equivalent to this characterization, and I'll show that very soon. If you want to show directly that this is true, just feed in any AB, and what do you get? You get minus BA. And certainly the dot product of those guys is just minus AB plus AB, which is 0. Okay, and this is just the standard way of taking a vector and rotating it 90 degrees. Flip the entries and put a minus sign in. Talked about that already, at least once in this sequence. Similarly, if we look at that 4x4 matrix of rotations, cosine theta minus sine theta, sine theta, cosine theta, and this time I'll cheat and just do the big zeros, and then cosine phi minus sine phi, cosine phi. Okay. Oh, let's actually have them be the same because I don't want multivariables here. Let's just say it's rotating the same amount, and just to have an example. And if I look at that, and I take the derivative at theta equals 0, I'm going to get again an anti-symmetric matrix, something whose transpose is equal to the negative. Remember, the transpose just flips across the main diagonal. That's interesting. Okay, so let's see if we can show that that's a general thing. Alrighty, so let's look at, so our characterization, geometric characterization, was that AV, and I'm going to use the dot product here, AV dot V equals 0 for all V. Okay. Well, first I'm going to show that that actually gives you something where I can let the V and W be different and give you an interesting characterization of that. Okay. Well, actually, first let me just express that in terms of transposes. Okay. So we got 0, which is AV dot V. Well, one way to take the dot product of two vectors is, say, if this is a column vector and that's a column vector, you take the transpose of the first one to make it a row vector and then use a matrix product. So this was a dot product. Now it just becomes a matrix product. This is a row vector times a column vector. And one of the things about the transpose that we need to know is that the transpose of a product is the product of the transposes in the opposite order. Okay. So this is what we know, is that if you put the matrix in between these two vectors, in between a vector and its transpose, then that's going to be 0 for all V. Okay? And let me go ahead and say what that means when I let the vectors be different. There's a clever trick. It's called polarization. And it says that, hey, if something is true for any vector, then it's true for the sum of any two vectors. So I'm going to take this guy and I'm going to plug in the sum of two vectors where the v was. And then I can use bilinearity. I can use distribute. So this is going to have 4 terms. I'm going to start dropping the arrows over the v's. It's getting tiresome. They're all vectors. So I'm just going to distribute this out. So here's the 4 terms. So here's the non-cross terms, and here's the cross terms. Okay. Now, what do we know? So we're assuming this guy. Let's assume this is true. And what I want to get is something that talks about how 2 vectors are related to A. Well, these guys are 0. Okay, I'm assuming that it's this infinitesimal rotation, so it has this geometric property that when I rotate v, it's by an amount that's perpendicular to v. That means these guys die. And then that's interesting. It says the sum of these 2 guys is equal to 0. Okay, so let's just rejigger this a little bit, though. Okay. These guys are just numbers. All these guys are the results of dot products, or equivalently a row vector times a matrix times a column vector. And if you look at the dimensions, it's just scalars. So one of the things you can do with scalars is you can transpose them, and they don't change at all. So I'm going to take the transpose of this guy. And now I'm going to use that rule about transposes. So this is going to be the transpose of everything multiplied in the opposite order. And notice, hey, the v becomes a v transpose in front. The transpose of A is back to A, and then the transpose of W is back to W. Okay, this is equal to 0 for all v and W, but I can then just collect that. That's A transpose plus A times W. Okay, so no matter what the vectors v and W are, then the product of A transpose plus A times this vector is 0. Now, let's just pick some really special vectors here. Let me just save that this is equal to 0 for all v and W. So, for example, 0, 0, 0, 1, 0, 0, 0, 0 times A times 0, 0, 0, 1 in a different position, quite possibly. That's equal to 0. A plus A transpose, sorry. Or A transpose plus A. What does this do? It's not hard to see that what this does is it picks out any particular row and column of A transpose A that you want to be, and they're all 0. Okay. So the only way you can have a matrix so that it multiplies by any column vector on the right and any different row vector on the left to be 0 is if it's the 0 matrix. Or in other words, it's an anti-symmetric matrix. Okay. So that's a proof that if I have this property that AV is perpendicular to V for all V, then it actually must be anti-symmetric. It's not too hard to reverse it, and in fact, it's an if and only if. Okay. If you kind of just look at the steps we did, they're mostly reversible. So it's not too hard to rejigger it into a bidirectional proof. So this is a very nice thing about something you can read off really, really well, easily, about just looking at the matrix. So that's a nice thing about infinitesimal rotations, is that just looking at the matrix and checking, hey, if I flip it across the diagonal, do I get negatives? Then that's going to be characterizing an infinitesimal rotation. Okay, so in particular, any such A is made from very special such A's. Let's say everything 0 certainly has to be zeros along the diagonal, because these guys are supposed to be equal to their own negatives when I flip them. Now I'm just going to pick any particular, let's say, row I and column J, and I'm going to put a 1 here. Oh, whoops. I'm going to put, say, let's see, I don't want them to be so similar. Let's say I is kind of near the start. Okay. Let's put a 1 here in the ij position. That means over here in the ji position, I've got to have a -1, and everything else is 0. Okay. Hopefully it's pretty easy to see that any matrix that has this anti-symmetry property, I can make as a linear combination of these guys. And so these are going to be, if we want to use a little bit of slightly more sophisticated linear algebra terminology, these are going to be basis matrices for the set of all anti-symmetric matrices. or in other words, infinitesimal rotations. They're all just linear combinations of these very, very special guys. And notice, of course, in 2 dimensions, we've already seen the one basis matrix. Any infinitesimal rotation in 2 dimensions is just some multiple of this guy. Basically, they just rotate at different, an infinitesimal rotation starting out at a different speed. This would be at a unit speed. Okay. So notice there's kind of a pairing. There's at least a formal pairing. If I want to tell you which basis vector to talk about, I need to pick an I and a j, or another way to say it is I pick 2 basis vectors in n dimensions, ei and ej. So somehow these fundamental rotations are paired up with pairs of vectors, not single vectors, not like an axis of rotation like in 3 dimensions, but pairs of vectors. Okay, so that's interesting. And then the anti-symmetry might be suggestive as well. Ooh, maybe that has to do with wedge products, that those are anti-symmetric. In the next part, I'll talk about how instead of having to do this all out in coordinates and explicit matrices, which is very nice and concrete, you can do it all without coordinates, which is always how mathematicians tend to like it better. And we'll get this much tighter connection between rotations and pairs of vectors, and we'll see that the hint of the wedge product is not at all misleading.